Right, so we know that you can use the catch state to denote a state. In this case, so we have this M is the eigenstate of harmonic oscillator. Okay. Suppose now we have a superposition of the zero state, ground state, and the first excited state. Okay, with this factor square root of 2. So how should we calculate the this factor? Okay, so first of all, this one is the brush state. Okay, if we write down this as let me put I right here. Okay, so that this can move. Let me put I right here. Okay. Okay. And this one actually now can be written as you put 0, change the 0 to the brush state. You change the 1 to the brush state as well. And there's I right here, but now this one will become minus I. You take the complex conjugate, okay? So that's one thing you need to be careful. So this one must be a complex conjugate. Okay. Now remember the brush state is the complex conjugate of the catch state, right? So that is something you need to be careful. Okay. So now let's try to calculate this one. So per psi and per psi now can be written as okay. There's R right here. Okay. So it's a product of the bra and the catch state. So this one can be written as 0 and 0 plus 0 and I times 1. Okay. So you can take this one as 1 and this I put right here. And you can have minus I and 1, 0 and plus minus I times I and 1 and 1. Okay. And divided by square root of 2 times square root of 2, right? I know that 0 and 1, this one is 0. 1 and 0, this equals 0. This is because of they are orthogonal. And this one equals to 1 because they are orthonormal, they're normalized. This is also 1. Okay, so the result just equals to 1 plus 1, or 1 plus 0 plus 0 plus 1 divided by 2, so equals to 1. Okay. Right, so this is the way to calculate this overlap between the two states. Okay. Right, so you can just follow the same procedure. If you have more states, you can do this similarly. Okay. Let's try another one. Let me copy this one. Per psi equals to 0 plus I 1 divided by square root 2. Let's try to calculate the expression value of this position operator. Okay. So we try to calculate this one. So this one equals to what? So again, this is 0. This is minus I and 1. Okay. And X operator, and this is 1 plus I and 1. Okay. So now you can again expand this one. Square root of 2 times square root is 2, right? So you have 0 x 0, and you have 0 x 1, and then you have the coefficient I over there, and you have minus I 1 and x 0, and the minus I, 1, x, 1, and I, right? So the first one is the matrix element x0, 0, and the second one is matrix element x0, 1 times I. And another one is minus I, 1, x, 1, 0, and then plus x, 1, and 1, and divided by square root of 2, right? Okay. But we have the matrix element 0, 0, this is equal to 0, right? Because the matrix, remember, the X matrix is something like this one. All the diagonals are 0. And this is square root of 1, this is square root of 1, this is square root of 2, this is square root of 2, and so on and so forth, right? And all the others is 0. And then divided by LC over square root of 2, right? And similarly, x11 is 0, the diagonal terms is 0. And x10 equals to LC divided by square root of 2 times square root of 1, right? 10 equals to LC divided by square root of 2 times square root of 1, okay? So you put this into this. The result is, this is 0. And this is I times LC divided by square root of 2. And this will be minus I LC times square root of 2. And then plus 0. Of course, this one is still 0, right? Because that term would cancel each other, right? You can also try to calculate another one. Let's say PHYS and momentum operator. So if it's a momentum operator, you can see that everything is similar. Okay, so this will be 0, and this will be I LC over 2, square root of 2. But now this one is a minus I times square root of 1. Okay, because the P01 equals to LC over square root of 2 times minus I times square root of 1. And P10 equals to LC, sorry, not LC, LC minus 1 times H bar. Square root of 2 plus I times square root of 1, okay? So now this is minus I times H bar LC to minus 1 times square root of 2 and plus 0. Sorry, this is times square root of 2 times square root of 2. It's not the right. So you put this together, you can see that this will be I times minus I just give you 1. Minus I times I also give you 1. Okay. So the result is just H bar LC to minus 1 over square root of 2, right? So that gives us the average of this state. So you can see that the PHYS state is the state that has 0 expansion value of position, but have a finite value of the expansion value of the momentum. Okay. But anyway, this is just an example to get us more familiar with those direct rotations. Okay, just to warm up. Okay. And today we're going to discuss the general solutions of the central force problems. So before that, we would like to have some mathematical preparation. Okay. And we're going to see how those operators can have simultaneous eigenstates, okay, if they commute. But first of all, we needed to learn that how to find the eigenstates of a matrix, of an operator by diagonalizing a matrix. Secondly, and then we say that if A and the B commute, okay, that means AB equals to BA, and then therefore simultaneous eigenstates. Right. So that's what we're going to do. Okay. And this one actually is related to the symmetry. Okay. And constants of motion, or in other words, say conservation. Okay, but later we're going to see this with more details. Okay. Right. First of all, let's review a little bit what is the matrix, right? So if I have an operator, for example, okay. So this is defined as M XM. Okay. So that's the matrix elements. Of course, this one depends on depending on the choice of the states, right? So we say that this is so this one is the matrix representation. And that's depending on the choice of basis. Okay. Right. So it's a representation. Okay. And the specific form of the matrix elements depending on the choice of the basis. So that means if you have different choice of basis, of course you will be different, right? So that's one thing. And second, I want to tell you another thing is that all physical quantities, for example, position, momentum, Hamiltonian, L squared, LC, okay, potential, so on and so forth. They all have emission matrix. So that means AMM equals to AMM complex conjugate, or this A operator, the DAG, equals to the transpose, and then takes complex conjugate just equals to the original matrix. Okay. Okay. So this is the property of all physical quantities. So they're all emission. So I can prove this one for X and P. Okay. And then you can follow the same idea. Okay. To show other operators, as function of this physical quantities should also be emission. Okay. Right. So for example, so let's look at the XMM. Okay. So this one, of course, according to the definition, right? Let's just use one-dimensional case as an example. You can easily join this one to the three-dimensional, okay, case. And this one, of course, can be written as right. That's very simple, okay. So now this one is nothing but just the inside of this one is nothing but just XMM, right? So this one just equals to XMM complex conjugate. Okay. So this one, so that means this X operator is emission. Okay. So that's one example. Let's also look at another example. momentum. Okay, so this one is defined as okay. And now you can see that this I actually is important. Okay. Okay. Right. So this one acting on the M function, right? So what we need to do is to try to see whether this one equals to M, okay, and the compass conjugate, right? So then let's take the compass conjugate first. So this one will equals to, okay, take the compass conjugate, that will be percent mx. And now this one is h bar over minus I, okay? So that's why I say this one is important, okay? And d over dx percent m compass conjugate. And dx, right? And of course, to make this one to be correct, you have to put the compass conjugate to outside. All right. But now this one is not exactly this one yet, because this one acting on the m, not on m, right? But now we can do this one. If the states are normalizable, we can use the integration by parts. Okay, for normalizable states. Okay, so that will give us a minus sign. So this one will equals to. Okay, so you have two terms. So one is right, and then another term is just so another term is going to be. Okay, let me write down this one more carefully. Okay, so you have two terms. One term is percent m x h bar over minus I, and percent m compass conjugate x. You take the age of this one and take the compass conjugate, right? Okay. And then another one is minus. Now it's percent m compass conjugate x. And now this is h bar over minus I. And now you have d over dx. Now acting on this percent mx. Okay. So this minus I comes is because of the integration by part. Okay. And of course, you finally take this one, take a compass conjugate, right? Okay. I made a mistake. And let me check this one first. Okay, so this one, because of it's normalizable, so that one must be 0. Okay. Okay, so got this one to be 0. Right? And then let's check this term that equals to minus sign. So what's inside is just a minus P M. Okay, and take the conjugate, right? So that equals to plus PMM campus conjugate. So you can see that this one is really important. If we don't have this minus sign, so that would not be correct, right? So that means, so we can also check this one is correct. All right. So now we can, so this is just 2 examples to show that okay, the physical quantities actually are image conjugate, okay? Okay, you can show other examples, okay, by yourself, okay? For example, you can try p squared, okay, over 2m. Okay, you can try x squared, okay? You can try something else, but anyway, using similar methods, you can show all the physical quantities are actually emission matrices if you have a basis, okay? So in this sense, okay, so we define the so if you have an operator A, it's called the emission operators. If you take any matrix as elements, okay, okay, equals to so this one is equivalent to this one, or it's also equivalent in Dirac rotations. We say that M equals to M, the campus conjugate, okay? Right, for any functions percent n and percent m, okay, as long as they are normalizable, okay? Right, so this is you know, the first thing that we're going to do, okay? Right, so next, since now we have matrix form, okay, actually we found the eigenstates, okay? Right, suppose we want to find the eigenstate. So a function such that an operator A acting on percent just equals to A and percent. Okay. You can either solve an PDE, okay, with boundary conditions, right? Such as the, for example, we have solved this one for the harmonic oscillator, right? Another way is that finding a matrix, okay, AMM equals to M and A and M. So we write down the state equals to summation of M, Cm, okay, expand percent in the basis M, okay. And then you can see that this one can be written as summation of M, Cmm and put A right here, right? But remember, this is a linear operator. Okay, so that means this one will equals to summation of M, Cm, and A acting on this one. Right. And now you can multiply M right here. So you can multiply M right here and then M right here, okay? Right. And this one will equals to summation of M, A, M, M, Cm, right? Wonderful. And suppose this is eigenstate. And we also have A percent equals to A times percent. That equals to A summation of M, Cm percent M, right? And now you can again do the same thing. Multiply M right here. Multiply M right here. So multiply M right here. So this one will equals to A summation of M, Cm, and M and N. So that will give us a data function because it's also normal basis, right? So that equals to A times Cm. So these two, they should be equal. Okay. Right. So that means summation of M, A, M, M, Cm equals to A, Cm. Look at this one. Okay. Take this one as a matrix. Take this one also as a matrix. Okay. So basically C just equal to C1, C2 is a matrix. Right. Okay, so the eigenvalue problem so that you find the eigenvectors of A, okay, you got a state Cn. This one determined, right? That one determined from this vector C1, C2, right? Because you have this C equal to A times C. So this is the this one called a eigenvector. And A is the eigenvalue. Okay. And then the percent just equals to summation of M, Cm, N, right? It's obtained, okay. Right, so this means so the eigenfunctions of A is equivalent to the eigenvectors is a column, there are columns, right, of coefficients, okay, of the matrix A. Okay. So then you can use the linear algebra the method is equivalent to this PDE method, right? PDE plus the boundary condition. Okay. And also you know that and this A is emission. So that means you know, it can be fully diagonalized. This is one conclusion. Secondly, A compass conjugate equals to A. It's a real number, right? So all the eigenvalues of this emission operators must be real values. So this is very easy to see from the linear algebra, but it's not that transparent if you use the PDE method. Okay. All right. Okay, so this give us another method to find the eigenstates of an operator. Okay, so you basically first of all transfer this one into the step one, have basis, and the two, find the AMM, the matrix, and three, diagonalizing this A matrix, right? So you got the eigenvectors, and then you got this eigenstates. Okay. Right. So that's another result we obtained. Okay. So now if you have two emission operators, this one equal to 0, that means A acting after B equals to B acting after A, okay, for any states, right? So that basically means AB acting on the static per se just equals to BA acting on the static per se, right? For any per se, okay. So now the conclusion is that they can be simultaneously diagonalized, okay, and the eigenvectors or the eigenstates are called simultaneous. Okay, so this is the thing that we're going to prove a little bit. Okay, so let's consider case. Suppose we have found all eigenstates of A. Okay, so we have A acting on the state A equals to A, this one, right? Okay, so but in general, now we can have a degeneracy. Okay, so M equals to 1, 2 until to D. That's to denote the degenerate states. So that means for each A, there are D states. Okay, right. So it's not necessarily eigenstate, right? So we have say this. We have say this one, for example, mx and y, right? So that can be the energy right. So this one can be degenerate if you have omega x and omega y are the same, right? For the isotropic harmonic oscillator in 2D, right? So you can, in general, you can have this one. But now you can see that if you, so the first thing that is, we found that BAM is also an eigenstate of A. So that's the first thing that we want to prove. That's very easy, actually. So we take this one as a state, right? So this is a state, and this is the operator, right? This is a cat state. This is the operator. The operator acting on a state, you still got a state, right? So you put A act on this one. Let's say So this one should be A and B and AM, right? Of course, right? But they are commutable, okay? So that means this also equals to B and A, acting on A and M, okay? But this is the eigenstate. Right? So that means this is A and AM. But this is a number. It's a real number. And this is a linear operator. Okay? So that means this one equals to A acting on this one, right? Okay? So look at this one. From here to here. Right? So it's not only the eigenstate, but also the eigenstate is the same. Eigenvalue. Right? So we have proved this one. Okay? And secondly, if D equal to 1, you must also have okay. The reason is very simple, because there's only, if D equals to 1, that means there's no degeneracy of A, right? So that means B and A1 should be proportional to A1, right? Because the A has only one eigenstate with the eigenvalue, right? Because A has only one eigenstate for A, okay? So that means A1 is also an eigenstate of B. So this one means simultaneous eigenstates, right? Okay. So in this case, if there's no degeneracy, so you immediately find that this state A1 is not only the eigenstate of A, but also eigenstate of B. Okay. Right. But of course, what if they have more than one states? Okay. The third case is that what if okay, and we know that all of this one okay, this one is the an eigenstate of A, right? Okay, with eigenvalue A, okay, and there's degeneracy. There's A1, A2, AD, right? So there are so many states, and if we have a state per psi written as a function, a superposition, Cj and Aj for j equal to 1 to d. And this one, we also have A acting per psi equals to A acting summation of j equal to 1 to d and Cj and Aj Okay, so this one of course equals to summation of j equal to 1 to d and cj and a and a act on a and j, right? And remember this one, and we give you an eigenvalue, so it's all a, so that means this one is also summation of j equal to 1 and d, summation of j and a and j, and this one is nothing but just a state, so that equals also a percent. Okay, so this one is also an eigenstate of a with eigenvalue a, right? Okay, and actually this is the form of all eigenstates of a. Okay, you cannot have other states or written in other forms. Okay, so this actually is all eigenstates of a with eigenvalue a can be written as this form. Okay. Right. So from this and this, so together, you must know that this B acting on this A M should equal to, a summation of Cj and Aj. Right. Because this one is eigenstate, so it should be written like this form. Okay. Right. And now you can act in, say, AM on left hand side. Okay. Okay. Sorry. So now you can say that now I can choose a state. I can choose a state. That's a summation of j, Cj equal to 1 and d. Right? So this one is already eigenstate of psi. And now, so if you choose these coefficients, okay, and see if we can do this. Okay, and now we have on the left hand side, this is right. On the right hand side, this is okay, and now you multiply on both sides. Okay, so you obtain that B AM AJ times CJ, do the summation of J, right? Okay, 1 to D, okay? That will equals to B and CM. And this one immediately got to something like a BMJ and CJ, do a summation of J equal to 1 and D equals to B and CM. So that is nothing but just a matrix. This is a D times D matrix. And this is a C coefficient is D times 1 is a column. That equals to B times, C1, C2, CD, right? Okay. And then you can see that so by that organizing the D times D matrix, okay, in the basis, right? You can find the D eigenstates, eigenvectors with eigenvalue B K. Okay, so that means you have B okay. And now this state per se equals to, let me call this K, summation of J equal to 1 to D and C, K, and J, and A, J. So they are simultaneous eigenstates, okay, of A and B. Right, so that means we have proved that not only for the non-degenerate case, but also for the degenerate case. So we can find the eigenstates, that are simultaneously eigenstates of A and also eigenstates of B, as long as this A and B commute, right? So that means we have this one, A and B can be simultaneously diagonalized. Okay, this is also quite a good practice of this matrix representation of the operators. Okay. All right. So QED, right? That's the end of this proof. Okay. We're gonna have more discussion on this. Actually, to show more examples of this by looking at those central force problems. Okay. That has rotational symmetry. Okay. But let's take a break and let's see if you have questions for further discussions. Okay. Right, so we're going to discuss the central force problems, and that one has a lot of symmetry. Okay. So we would like to examine this relation between the symmetry, okay, and the commutability of operators, and then we have simultaneous eigenstates, and that one relate to the conservation. Okay. And mathematically, this is called the Lorentz theorem. And we know that in classical mechanics, okay. So if I have a symmetry, for example, if I have H, say, independent of X, right? So we say that this is the translation symmetry. Right? Or independent of angle. We know that there's rotation symmetry. Okay, and so on and so forth. Right. And if I have this one, and then we know that there will be quantity, the momentum, and the Hamiltonian equal to 0. Okay, for a system with translational symmetry. Right. So let me use another way to do it. Okay. Right, for this one, we know that the Hamiltonian and the momentum would have a 0 Poisson bracket, right? And for the rotation symmetry, we know that the Hamiltonian and this Lx, Ly, Lc, the angular momentum components, okay, will have a 0 Poisson bracket. Okay, so these are the Poisson brackets. Okay, so that's actually pretty easy to show. Okay, for example, if we look at the Hamiltonian and the P, that equals to partial P, partial X, partial H, partial X, partial P minus partial H, partial P, and the partial P, partial X. Okay, and then you can see that this one is 0, and this one is 0 because you have a translation symmetry, right? Okay, so this one will lead to this. Okay, so this means and d over dt of the momentum equal to 0, right? That means the momentum is a constant of motion, or is conserved. And similarly, you have and this one is 0. The angular momentum is 0 if you have a translation symmetry. So this is what we have in the classical system. And correspondingly, we actually have similar things in quantum mechanics. Okay. Of course, if we have the Hamiltonian, say, independent of, for example, X operator or theta phi, right? Or some other cases. And for this one, we know that you have translation symmetry. Okay, and for this one, you say that we have the rotational symmetry. Okay, right? You can see the examples, right? For this case, and for this case, we have say that's a kinetic energy. So this is the central force potential, right? Okay. Okay. And then you can see that because you have this translation symmetry, you find that the Hamiltonian and the momentum operator actually has is zeros. Has 0 commutator. Okay. And similarly, for this one, you have actually the Hamiltonian commutes with all the components. And also, of course, the angular momentum squared. Okay. So I should know that, point out that these two actually are related by Dirac. Okay. Okay. Dirac showed that there is a correspondence between the Poisson bracket and the commutator in quantum mechanics. Okay. Okay. And then from this we know that you can have H and the P has simultaneous eigenstates. Okay. Or you can, in this case, you can have H and L square and LZ. Okay. But we can have these three objects can have simultaneous eigenstates because they commute, right? But you cannot have Lx, Ly, or Lz, the simultaneous. Eigenstates, okay? So not for Lx, Ly, or Z. Okay, sometimes because for example, Lx and Ly, they do not commute. Okay. So these five operators, they do not mutually commute, but only H and L square. And one of the components, okay, for example, Lz, okay. Well, of course, you can choose also Lx, okay. And now, so that means, so we can have H per psi equals to energy per psi, right? And the P and per psi equals to H bar K per psi. So this means this is a stationary state. Okay. So that means this is a certain momentum. So that means you can have a system in a stationary state so that the momentum is certain. So this means for any state, the momentum expression values will be time independent. So that's conserved, right? And similarly, okay, if we have a rotation symmetry, okay, right? So that's something we have now for the symmetry and the conservation. Okay, so we go from here to here, right? Okay. All right. So you can see that if you have two operators that commute with each other, and then we can diagram them simultaneously, especially if one of these one is Hamiltonian, and then we say that this commutability actually related to the symmetry, And this symmetry, you know, will lead to this conservation, okay? Right. Some of you may ask, how is this operator related to a rotational symmetry? Okay. So I'll give you a hint. So remember LZ right equals to h over bar I partial phi. Right. And let's try to apply this one to a wave function. Let's we have a wave function x, y, z, and then we can write down this one as r theta phi function in the spherical coordinates. Okay. So in the spherical coordinates. And let's see what will be the effect of this one, right? So of course, LZ, you know, act on this per se r theta phi is nothing but just h bar over I and partial phi. Very simple, right? But if you times I times h bar right here, so that will cancel this one, right? Or if you put minus right here, so there will be minus right here, right? If we do this by m times, so this just gives you m times, right? Okay. Okay. If you put m, one m factor right here, so you just put a one m factor right here, right? And then you do a summation of all these terms. And acting this one on the per side. So that will just equal to summation of m equal to 0 to infinite 1 over m factorial minus 1 to the m factorial partial m over partial phi m and per side. Okay. Right. Suppose you can also put a number right here. Let's say alpha to the power m. So you put alpha to the power n right here. So on the right hand side, this is nothing but a Taylor expansion, right? So this just equals to per side r theta phi minus alpha, right? Okay. And on this one, you are just keeping applying this angular momentum operators. So this one actually equals to e to minus I over h bar alpha and LC is the exponential function of this operator acting on this one. So you can see that these two, okay, so this is nothing but just a rotation of per side about the z-axis. Right. So that's why we say that this angular momentum, so it's this one generates rotation about the z-axis. And similarly, you can say that if you have x and y components of the angular momentum, that actually will generate rotations about the x-axis and the y-axis. Okay. So you can say if you have a state, that's an eigenstate of the LZ and also eigenstate of the Hamiltonian. Okay. So if LC acting on psi equals to a constant, let's say m h bar and psi. And so look at this one, right? So you can see that from this one, you know that E minus I alpha over h bar and LC acting on this psi. That's a rotation, right? So this way equals to, because this is eigenstate, so that equals to e to minus I alpha times m and the psi. Okay? This is the same state. Okay? Because there's only global phase factor. And this one, of course, you can see that the time evolution of this one will be ht over h bar and psi. That way equals to e to minus I, the evolution of this one over h bar. It's a psi. It's all the same state. Because all of this one are called the global phase factors. Right. So you can see that if we have a system that's symmetric on the rotation, so then you can simultaneously diagonalize the angular momentum and the Hamiltonian. So the state can be rotational symmetric and is stationary. So in this case, you have LC is now a conserved, right? So this, you can see that from this one, we see the relation between the rotation symmetry and the angular momentum, okay? Right, so that's just a first flavor of this relation between the, an operator, and the symmetry, okay? And similarly, you can do the same thing for the momentum, okay? Right, so we can have more of this one. Okay, so we cannot cover too much on this, okay? All right. So let's check one example. Okay, let's look at the isotropic 3D harmonic oscillator. Right, so let's consider state E1 that equals to h bar omega plus 3/2 h bar omega. Right, remember that equals to nx plus ny plus nc, okay, times h bar omega plus 3/2 h bar omega, right? And this one is the 0-point energy. This one is the the energy because of the occupation, right? So you have three states. So the degeneracy d equal to 3, right? So you can have states 1, 0, 0, 1, 0, 1, 0, and 0, 0, 0. Okay. Right. Let's write down the states. It's actually pretty simple. Okay. It just equals to the psi 1, 0, 0 just equals to psi 1x. Psi 0 y and psi 0 z, right? So that equals to proportional to, okay, let me forget those coefficients. And x e to minus x squared over 2 and minus y squared over 2 minus z squared over 2. So that's nothing but just x e to minus r squared over 2, right? Very simple. And similarly, you have psi 0, 1, 0 that equals to y, a proportion to y to r squared over 2. And psi 0, 0, 1 is proportional to z e to minus r squared over 2, right? Okay. So you can actually call this one, let's call this one x, and call this one y, and call this one z. Because, otherwise they're the same. The only difference is just they have this x, right? So let me just, for shorthand notation, just denote this one as x and y and z, okay? Okay. All right. And of course, as I said before, right, these are the eigenstates of Hamiltonian. So you have this E1x and Hy equal to E1y, but Hz equals to E1z. Okay, that's degenerate. Well, how about the LC? Okay. So the question: do we have simultaneous eigenstates? And we can check this one. That's very easy. Okay. We can use the spherical coordinates. So LC equals to, you can see that this is h bar of I partial phi, right? And look at the x. So that's proportional to x e to minus r squared over 2. So that's equals to cosine theta, so sin theta, cosine phi, and r e to minus r squared over 2, right? And y is y e to minus r squared over r. That's sin theta, sin phi, e and r to r squared over 2. And c is going to be c e to minus r squared over 2. That equals to cosine theta, r e to minus r squared over 2, right? Okay. And now let's try to apply this one to see if to check whether this one are eigenstates. Okay. So now we're going to use this one to check this. So LC action, let's take a Z. That's very simple. You can see that Z does not depend on phi, right? So that means if we do the differential, so it's proportional to h bar of I, cosine theta, r e to minus r squared over 2. And this obviously is Z. Okay? So that means Z is a simultaneous eigenstate, right? Of H and LC. Okay? And how about X? So that's h bar of I partial phi. Okay. Now this one is cosine theta, sin theta, sorry, cosine phi, and then r e to minus r squared over 2. And now this phi action this way will give you sin phi, right? Minus sin phi. So the result is going to be that equals to I times h bar y, right? Okay. So Ly, and so LC on the y state, h bar of I partial phi. Okay. Sin theta, sin phi, e to minus r squared over 2. So you do the integration, do the differential with respect to phi, and then this gives you cosine phi. So that is nothing but just x. So that gives you minus I h bar x. Okay. Right. So from this one, you got a matrix. So you change x to y. So this one will give you minus I h bar 0, 0, and I h bar 0, 0, 0, 0. And you're acting on the z. Okay, that's 0. Right. This is very easy to diagonalize. So the eigenvectors. First of all, it's actually very simple. It's 1 over square root of 2, I 1 over square root of 2. So it's 0. Right? It's very fun. And eigenvalues. So this is going to be h bar. This is going to be minus h bar. This is going to be 0 h bar. Okay. And then let's form the eigenstates. And then so you know the states. Let's say E1. That's the eigenvalue of the energy, and the h bar. Okay, so that's the eigenvalue of the angular momentum in the z direction. So that way equals to 1 over square root of 2 x minus plus I over square root of 2 of y. So you put that one together, that will be 1 over square root of 2 x plus iy e to minus r squared over 2. Okay. So this one just equals to 1 over square root of 2 and r e to minus r squared over 2 times e to I phi. And if you have another eigenvalue, say if it's a minus sign, so you can have plus or minus, and this will be minus, right? And this will be minus. This will be plus or minus. So you got the two eigenstates, and of course you have the third one, that is E0 h bar, that equals to just C, right? So that is it's nothing but just r equals to minus r squared over 2. Okay, right? So this way you can find the simultaneously. So these are the simultaneous eigenstates of H and LC. Okay. Right. So now you can see that indeed we can use this diagonalization of matrix method to define the states, and you can also show that these states. So you can write down this one basically as E1 m times h bar equals to the proportion to r e to minus r squared over 2 e to plus I m phi, for m equals to 0 or plus minus 1. Okay, right? And these states evolves as so you can say on this. This is conserved, right? Because these are eigenstates of this one, and so you have this one to be stationary states. Okay. Which one? That's r sin theta. Oh yes, you're right. Sorry. This r right here, right? Which one? Oh yes, thank you. Yes, you are very, very right. Important, actually. So this one actually is not correct. This one, we say there's a function that depends on m theta, right? Yes, thank you. So, but we are not concerned with theta at this point, okay? All right. So this is just one example of how to diagonalize this Hamiltonian and angular momentum using simultaneous eigenstates of Hamiltonian and angular momentum by diagonalization for matrix, right? Okay. Okay, so now I think we are ready to discuss the more general features of the central force problem. Okay. Right. So we know that force equals to right. So if this is a central force, so this one is parallel to R. So that means this V X, Y, Z must be a function of R only. So it's independent of theta and phi. Okay. So this one, first of all, it's a special force. Okay. Not always true, right? Of course. Right. For example, it's not true if omega x does not equal to omega y, does not equal to omega z, right? In the harmonic oscillator. So that's called anisotropic ion trap, for example. And this actually is often the case in experiments. And secondly, nonetheless, it is important. Okay, it's actually a model for many problems. Obviously, you can have isotropic trap, right? A hydrogen atom, okay, like a sodium atom. Okay, if you look at the the electron of the outer shell, okay, it also feels this kind of central force. Right, you can have Yukawa potential, for example. Okay, so there are many cases that this model can apply. Okay, and of course, it has obviously rotational symmetry. Right. So in classical mechanics, we know that all of this one has 0 Poisson bracket. So that means okay, that's the conservation. Angular momentum, right? Okay. All right, so this is so obvious. And now let's check quantum mechanics. Right, the Hamiltonian equals to px squared, the operator py squared, and pc squared over 2m, okay, and plus Vr, right? And this one can be written as minus h bar squared over 2m, partial squared, partial x squared in the Cartesian coordinates. Okay. Right. And it's easy to check. The potential with this one should be 0. And the potential with this one should be 0. And the potential with this one is 0. And so of course. Okay, so let me check one for you. Okay, so let's check, say, for example, V and LC, right? So this one equals to, say, VR H over bar I partial phi, right? So that equals to VR H bar of I partial phi minus H bar of I partial phi and VR. Okay, so this one, of course, acting on not only on this but also on the otherwise. But this one can be moved to this one because this one the potential does not depend on phi, right? So that means the two terms just cancel each other, right? So it's very easy to check. And so Z is not a special, right? Okay, it's not special. So that means you must also have a V Lx y should also commute. Okay, and if we commute with all the components of this LZ, so you must have V commute with the square of this angular momentum, right? Right, and we all also know that before, so if you have free particle, actually the angular momentum is also conserved there. So you also have okay, so you also have this P squared and Lxyc. We have done this one before, okay? This one should also be 0, right? Okay, so with all of this one, so you have the important effects is that Hamiltonian commutes with Lx, Ly, and Lc. They're equal to 0. And the Hamiltonian commutes with this one. But of course, we have Lx, Ly is not 0. And Xyz and for others, right? Okay. So this means, so we can choose for example, H L squared and LC, okay, eigenstates simultaneously. Okay, right? So that means, for example, we can write down a state, the simultaneous state eigenstates of the Hamiltonian and L squared and LC, okay, can be labeled as M, L, M, okay, so that the Hamiltonian acting on M, L, M, okay, will just equal to energy, say, okay, so that's energy. Okay, so this M is called a principal quantum number, okay? And this one should also be eigenstate of the angular momentum squared. Let me just write this form, okay? And the h bar squared is because L squared has the dimension of h bar squared, right? So this is going to be dimensionless number. Okay, so this L is called a angular or orbit or azimuth quantum number. Okay, the values of L is to be determined. Okay, right? Because at this point we can say, and this one just by convention, okay? We just write down this as L times L plus 1. And later on, you're going to see why is L times L plus 1. It's not something else, okay? But in general, you can just write this as a lambda, okay? So you can, if you want, or you can just use a lambda to replace, okay? Right. So you give it a lambda, the eigenvalue, so you can solve, L, right? So it doesn't really matter. And LC act on this one because it's simultaneous eigenstate. So let's write down this one as M H bar, okay? Because H bar is just a dimension, okay? And this M is called a magnetic quantum number. The reason of this one is that historically, the different LC states were, distinguished in energy if you apply a magnetic field in the z direction. Okay. Right. So that's the labeling of the states. So the question is, what are the solutions? Okay. So M is what? L. What are the possible values of L? And what are the possible values of M? Okay. Right. So let us stop right here. Okay. And next time we're going to find out what are the possible states which are labeled by these three quantum numbers. M, L, M. Okay. Called a principal or angular or magnetic quantum numbers. And what are possible values of M? Okay. What are the possible values of L and the possible values of M? Okay. In the general central force problem. Okay. And after that, we are going to apply this one to hydrogen atom problem. Okay. Once we have solved this problem, then we can consider a special case. That's a hydrogen atom. Okay. So let me stop right here and see if you have questions.